Hello everyone, I'm Cole.
And I'm Putu.
We are
May.
Yes, today we arrive at characteristic X-ray. Sleeping time?
No, not this
Time
time.
to sleep?
No.
Don't sleep at all.
Yeah.
So, characteristic X-ray.
This one is the continuation from the previous about the continuous X-ray.
Right?
And I think the characteristic X-ray has some different term.
Right,
Maybe
sure.
in accordance with the previous one is a continuous, so this one is discontinuous X-ray, right?
Discontinuous X-ray.
And there's one more term also, the fluorescent X-ray, right?
Right.
Yeah, usually term used for characterization of materials.
자, let me draw representative, the curve, the y-axis should be intensity. X-axis should be
the wavelength.
Wavelengths.
Should we use nanometer?
Nanometer scale all the time.
Okay.
And if we just apply certain voltage below some critical level, we can see very smooth here like this.
This one is the typical of the continuous X-ray.
Right, typical of continuous X-ray, and then
Yeah.
we can use it for medical purpose.
Right.
And then we just increase. Okay, voltage will be increased and further. And what happened? The height of this hill increase.
But the shape similar.
All right, shape quite similar. And then we can meet some critical voltage.
Critical voltage.
Over it, what happened?
I can expect there must be something which is the discontinuous X-ray.
Right. Characteristic X-ray appears from the moment, and then so this one peak here, another peak here. This one. It's not good drawing. It's not good drawing, and then. So here and then there are two different positions. This position, this position. Yes, we can say discontinuous what? Characteristic X-ray.
Yeah. Let's use the characteristic X-ray.
So what about that? We must give a name.
Yeah, this one is K alpha, I think.
K alpha, and this should be
K beta. This
beta.
one I always see in my result of XRD.
Right. This is a very important one, and then.
Right.
So what about can I give some examples of the K alpha value for several metallic material? Okay, starting from
using from
copper and chrome,
cobalt.
Right, that's true.
Molybdenum also.
Right. Okay. So let me do the wavelengths and then K alpha, and then first one, and then chrome. Atomic number should be 24.
Yeah, right.
It's correct. And then wavelength should be.
I cannot remember.
It's very difficult. 229 nanometers.
Oh, okay.
The next material as a target is cobalt, and then
27.
Oh, you remember all periodic table?
This one is commonly
I
see, so I cannot remember everything.
Number is 17.
Oh, it keeps decreasing.
Decreasing, and then. And next one is surely, and then copper. Atomic number is 29. And you know this number, right?
Oh yeah. This one commonly used 0.154 nanometer.
Right, that's true.
I'm proud of myself.
Many testing, you are required to this kind of number in many testing, midterm, final test, high school and middle school, university, and then. And the last material as a target is molybdenum. 42.
Yeah.
Wavelength should be decreased, and then.
Yeah, I think it should be decreased.
Approximately 1 nanometer. Right. So we're just talking about K alpha value. And then we can see something very interesting point, and then look at that. Atomic number increase. Right?
This tendency. I see why you use this kind. You write that way, Professor.
Yes.
So the atomic number increase,
Increase.
but the wavelength decrease.
Decrease. Okay. How can we do this one? Okay.
Where are you going with this, Master?
This one is higher. The wavelengths. And then wavelengths and energy, they are inversely
right.
proportional.
So if the wavelength decrease, actually the energy should be increased.
Increase this energy, it become higher. From the equation, as you know, but the put to, can you explain physically why molybdenum atomic number is 42 show higher energy
I think
condition? And then
someone give me some kind of
very useful explanation, and
yeah, some easy termination also.
using some kind of bricks or some story of the apartment, and then
I think book, sir, in terms of a books, sir. So I think you can, in that case, you can see that the number of atom we can relate as the number of electron, right? So the number of electron we can associate with the book, sir. So the stack of book. So if the number of atom is increased, the number of stacking book should be also increased.
Right.
So if we try to remove the bottom of the book, the first book, the image, the 3 stacking book.
Okay, here this book, and then
if we try to remove that one, I think it will be
easy, right?
Yeah, easy.
But what about this one?
Yeah, if we try the second stack of books, I think it will be surely more difficult.
More difficult.
Yeah.
That's why more energy will be required.
Right.
To gain these kind of things.
Yeah, this really easier for me to recall.
So that's why we just back to our histogram, and then Professor just said like that, and there must be specific range, specific value for the voltage, and then above this one we start to take a look at the formation of a characteristic X-ray. So we can say this is critical acceleration voltage. Simply critical voltage.
Yeah, usually I didn't take too much attention because this one is in the machine.
Right. So there's some value critical voltage before the critical voltage. We only see
of course that one, the continuous X-ray.
Right. Yeah. Continuous X-ray. Yeah. This is a continuous X-ray region. And then above the critical voltage,
surely we will see both the continuous X-ray and the characteristic X-ray.
Right. We can see the continuous X-ray here and together with characteristic X-ray. 자, continuous plus characteristic X-ray together. That's why the calculation of critical voltage is very important. And we can know there is some kind of minimal level of the voltage to gain characteristic X-ray. For your interest, and then I also provide more information, and then the copper. This critical voltage is around 8.98 kilovolts. Roughly you can say, and then 9 kilovolts, and then in the meantime, molybdenum is approximately 20.01 kilovolts.
I can expect that. Should be higher because it needs more energy to knock up that electron. Right?
From this explanation, everything is consistent.
Now become more make sense.
Okay. There are 2 different stages until we just gain the characteristic X-ray. The first one, elimination of electron.
Elimination of electron. I think this one is associated with the movement of electron from its orbital.
Especially from K shell.
I see.
The first orbital, right?
Nearest to the
nucleus.
Yeah.
I see. So that's why we started with the elimination of electron, and next stage is to be shift of electron.
Shift. Okay.
Shift of electron between orbital, between shell.
This one is quite interesting.
Mm.
So I think some story like some electron likes to take over some another
Right,
place
that one and
occupied.
that had normally happen in a library, and then there's
Yeah.
no more space, and then like a hoppers, and then we just move here, someone move there, like this approach, and then
In my case, I usually see in cinema also.
in Indonesia, right? So let me draw the orbitals 1, 2, 3,
Okay.
and then the other
This
one.
is where the electron resides.
Right. Quantize, and then
Yep.
자, it's K shell. The first one is K shell,
Right.
L
So
shell,
the L shell and then the M.
M shell. The same thing, K shell,
K,
L shell,
and
M shell. And then there's one electron. Now, first of all, we have to eliminate electron that stay in the inner cell, the K shell. How? Yes.
We shoot some incident electron.
Right. This one, incident electron. And then how this electron?
This electron get displaced or eliminated.
Eliminated from the title, and then it's eliminated. So we can say this is photoelectron.
Right. Photoelectron.
And then can you imagine some very, very super scientist
Oh wait.
who received a Nobel Prize before?
Very.
No, Einstein.
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 That one is the famous one. Why did I forget?
Einstein. Right, Einstein. So one electron here. What about that? On the right side, and then the electron here.
Yeah.
We want to eliminate this one, and then we can give incident beams, and then this is moving out.
Right.
Can you tell me, and then which one? This case, which one is more difficult?
Surely it must be the first case.
First case.
Yeah.
More difficult means, and then need more energy.
Yeah.
That's why this is the most difficult. Energy level is high. This side, and then. So once again, and then by combining previous one, and then I can summarize. There's some kind of connection. This is very, very useful. So one of our conclusion from here is atomic numbers. Atomic numbers. Normally we can say the G value is increased.
Yeah.
This means.
Do you think the energy required to remove the electron or eliminate the electron should be also increased?
Right. So that's why energy right here, and then okay, let's say critical voltage.
Yep. Let's use that one for the
acceleration voltage.
Light, yeah. Acceleration voltage.
Voltage increase, right?
Right.
This should be same as. What about speed of electron?
The speed of the electron, yeah, surely you need more higher speed of electron.
Yeah.
But surely cannot exceed the speed of light.
Yeah, sure. And then eventually elimination of electron become elimination of electron.
Elimination of electron.
Yes, high possibility. So that's why we must give high voltage, and then in the case of some matters whose atomic number
is high. Right.
Understand?
Yep.
This is the first one, and then we need to go to shift of electron between the shell. What about that? So this is the K shell.
The shifting of electron.
Mhm. And then M shell. Put 2.
Yeah.
How many subshell in M shell?
In M shell or L shell?
Sorry, L
L
shell.
shell.
L shell. It's not M.
In L, I think it's well known. 3 also.
3.
Yeah.
So 1, 3, 3. So L1, L2,
2, yeah,
and
L3.
L3. Above L, and then we can see LM.
Yep, right.
M shell. Yes. We can draw this kind of orbital stage and then. 자, what about that? Some electron. 자, here. 자, just in case. Okay. 1, 2.
It starts to get complicated this time.
It's very complicated then. So that's why I need more time.
You need to arrange the electron here, right?
Right.
Okay. 2, 3, 8. Oh, right. 8. I think you cannot draw all the electron in M, right?
Right, it's impossible. And then, how many electron in K shell?
Surely 2, sir.
2. There must be equation and then 2 n square.
Yep.
So K the kind case and n should be 1. That's 2.
Yep.
How many electron in L shell and then?
Should be 8. Sir.
Yeah, n is 2. That's why.
Yeah.
8.
You memorize this number in high
How
school.
many? Look at that. 1, 2, 3, 4, 5, 6, 7, 8. 2 for L1, another 2 for L2, and then next shells have 4.
Right.
And M, how many? Just in case?
18.
Right. So 18 right here and then.
Oh, it's so big.
자, and then I'll just start from here and then 자, this electron from the L3 subshell and then. And this can drop.
Drop to
K.
K orbital.
All to the K and then this is very critical. And then we can call it K alpha 1.
Oh. From 3 but K alpha 1.
Right.
Okay.
And then second, and then we can think about these atoms.
On the L2.
This atom also down here.
Should be K alpha 1. Alpha
K
2.
alpha 2.
Right. I think just limited
before
to
that and then I missing one point and then there is electron, right? So instant beam and then this electron eliminated.
Oh, yeah.
There must be the hole. That's why this electron above and then drop down to that kind of level and then. So what about we just think about this one.
Okay.
From the M shell.
Wow, from the very high.
Very far.
자, go down all the way to K.
K. And then there should be K beta.
Beta, okay.
K beta.
So all from the L level, all become alpha.
Right.
From the M, beta. Okay, please.
Right, that's true. And here, it's very confusing point that energy, K alpha and beta, we know that K beta is higher. But the intensity in X-ray spectrum, K beta intensity small.
Very small, right?
Smaller as compared to K alpha.
That's why you draw.
I
that
draw
before.
intentionally. Right?
Scientifically accurate.
And then another one about this atom down to here and then.
To the L.
L. And then we can call this
L something because the target is L.
L
Alpha.
So down. And then maybe the more interesting than I just draw. K alpha, this one, and going down here. And then there's an X-ray. This one is K1, K alpha 1.
The X-ray.
This one, K alpha 2 X-ray.
This one the characteristic, right?
Right. And L alpha, this one. So that's why I just write it down. the name of characteristic X-ray from the specific level between the some specific subcell of octa and then.
Right.
Understand?
Yep.
So here this one the question and then we never talking about K alpha 1 and K alpha 2, right? But I only draw K alpha. Also, you just carried out so many X-ray diffraction before.
Yeah.
Did you remember K alpha 1, K alpha 2 before?
I think I saw the glimpse of that answer, but the value between them is actually quite closer for the case of copper.
Very close to each other. That's why. For pure physics scientists, and they think about it, and this is very critical. But normal science engineering, we just use this kind of things as a initial wavelength. That's why consideration of just look at them. This kind of gap is not so significant. So simply we can say K alpha 1, K alpha 2, similar each other.
I see now. Because the level of the on the L orbital, it's quite close to each other. Yeah.
Right. That's why. But still, I want to give you another implication about K alpha 1, K alpha 2 to determine K alpha, the real value, and then here, and then even if the wavelength of K alpha 1, K alpha 2 is identical, but intensity is different. So I means the intensity K alpha 1 versus intensity K alpha 2. And then I can write it down and then intensity K beta. But here I don't like to write down L alpha. It's so small, that's why it's almost negligible.
Right.
The ratio, this one, is 100, and then there should be 50.
So we know the K beta should be much smaller.
Yeah, smaller than this one. That's why the final equation and then K alpha value, the ratio is 150.
Like
2 versus 1, 2 times higher.
Yeah.
So as a calculation, 2 and K alpha 1 plus K alpha 2.
I got it. So this one is actually they try to make it simpler, right? Instead of just considering two kind of K alpha, they use K alpha for average, right?
Right. The considering the mass balance and then so considering the intensity of these two values and then we give this kind of number. But nevertheless, K alpha 1, K alpha 2, they are all identical each other. And then, so it's the difference is almost negligible.
Right. But you explain this just to make sure that the flow is understandable, not just like receiving.
But
you
nevertheless,
very well.
You still have some kind of argument. You just say it's negligible. Please give me some kind of example. Okay, I want to provide example. The copper case. K alpha 1, this value is so small. We just say 0.154, right? This number.
This one, the number we use.
And then this one. K alpha 2, this value is same. 4 and then 4.
Very small.
0.0003. 1, 2, 3. Please wake up. It's not a sleeping time.
Right. As you always mention, for material scientists, this one is negligible.
Negligible. Right. We can neglect this value. But scientists in pure chemistry and physics, this is a very critical number.
Right.
Okay. All finished. What's that?
No. I believe there's one more thing.
One more thing. What is that?
Auger electron?
Auger electron?
Auger?
No.
Auger?
OJ electron.
OJ?
OJ.
That's how you... The writing is right?
Yes.
So that's how you spell it. Okay.
Ogre, why?
So-
These scientists from France and then French scientists,
Ah.
they feel OJ, not ogre.
I always fail in spelling. Like the
Actually, I
first
also
video.
attended some kind of class on YouTube
Mhm.
made by some scientists out there, and they just simply say ogre and then what's ogre? OJ.
OJ.
Okay.
OJ. OJ. Okay.
OJ electron is very important. Actually, this is a really last part in characteristic X-ray.
We are near to the end.
Yes. I need more patience. And then
Another
I just
orbital,
put
okay.
orbital again. 자, it's a K shell,
Yep. And then
L shell,
and then M.
M shell. Where is our target electrons? In K shell, right?
Right.
Mm,
It's the most difficult one to remove.
right. But we need to remove this one.
Incident electron.
Incident
come into
electron
play.
by the thermoionic effect,
Yep.
right?
From the tungsten thermal phenomena.
So, and then meet together, and then previous electron that was occupied in the K shell, they should be moved
Yeah. Eliminated.
out there.
Elimination.
So
Yeah.
eliminated there.
Yeah.
So,
Come
and then
photoelectron.
photoelectron.
Yeah. I like this one. From Einstein.
And then this can be the vacancy, right?
Right.
There is no electrons and occupying this place, and then what about that? There are some electrons near to this area,
Right.
and then all they take the chance, and then okay, let me go over there, and then this one
Yeah.
move down
This
here.
is the one you mentioned before. The
Shift
shifting, right?
of
Yeah.
the electron
Right.
between the shells, and then
And while they shift, they emit something. The
Right.
yellow things you draw before.
this one,
Photon.
photon, X-ray, right?
X-ray. Yeah.
X-ray, and then 자, photon emission.
Now, where are you going to lead us now, Versa?
X-ray.
Photon emission. Yeah,
This X-ray is not continuous. Characteristic
X-ray.
X-ray.
Right.
So what about that? This X-ray move in this way. Move in this way. And then occasionally they just meet some electron over there, out there, and then.
There is this scenario.
What happened?
It hits the electron.
Yes.
And
then binding energy between M and the nucleus is so small, right?
Right.
So by these energies,
I think it's enough to knock the electron away, right?
Right, that's true. That's why this electron can be moving out.
Get eliminated.
Eliminate.
Also, yeah.
So this one can be OJ electron.
This one is the OJ electron.
Right.
OJ electron.
OJ
Right.
electron. So what about that? Another shell. This path of choice, not this become the
this one also
vacancy.
vacancy. Yeah.
So another electron.
That electron wants to shifting also.
Yes. And that's all. Also is a generate X-ray. Right? In that kind of way. And then.
Yeah, I think I'm not too familiar with this one because it's rarely used in experimental, right? The OJ electron.
Really? No.
Really?
It's a very critical aspect, and then OJ electron spectroscope, and then. So this is very useful to determine, and then surface chemistry, and then they can provide us very useful information. The matter. The travel distance of the electron is so small, and then within 1 nanometers, 2 nanometers.
Wow.
That's why material is very depth enough, and the characterization this should be absorbed inside the lattice structure.
So the experimental should be including some substrate that's very thin, right?
Yeah, thin material. This is the OJ electron. As far as I know, Pierre OJ, he 1990 something, he passed away. And then I just believe that he's one of the finest scientists who close to Nobel Prize. But unfortunately,
He didn't get.
yes, that's matter.
He's genius actually.
So today we are going to talk about characteristic X-ray together with continuous one. And then there are many useful information, right? More the K
It's
alpha,
really useful.
K beta, and by utilizing some kind of concept coming from the apartment, a stack of books, right? And also we arrive at some kind of audio electron.
And your explanation is too good to be true.
Thank you. And then hopefully, and then this video clip can be useful for our viewer and subscriber.
Surely for me it's useful.
Okay, here is still one question, and then we gain the two different things, K alpha and K beta, right?
Right.
Still K beta. K beta, K alpha, they have different wavelengths.
Right.
They exist together during our experiment. Our experiment is not rigorous.
Right.
That's why next part we can talk about how can we eliminate K beta in order to gain pure K alpha wavelength.
So K beta is like
impurity and then
unwanted child.
Right. Not that way.
Okay.
Okay. The moments. Okay. You guys see you.
See you
next time.
Next time.